part of the mystique of mathematics is that it's very abstract. It doesn't seem concerned with the world, with what's going on. But this can be a double-edged sword. My guest this week, Minhyong Kim, has said that maths can suffer from being an ivory tower within the ivory tower that is academia. And Professor Kim sees mathematics as part of a continuum of disciplines, of physics, chemistry, even logic, philosophy and literature, all of which share a goal of ultimately trying to understand the world. Mathematics is no different. It is connected to the world in that same way. Minhyong Kim is professor here at Edinburgh and also Heriot-Watt universities. He's the Edmund Whittaker Professor. He's the director of the International Centre for Mathematical Sciences, and we'll also talk about the Centre of Mathematics for Humanity, which he also directs. More than this, he is a very accomplished mathematician. I am just someone who makes semi-popular videos about mathematics and philosophy and other things. I do not contribute anything to this field, but he is someone who has made genuine contributions, particularly to the area of diophantine equations. And if you work in that field, you've probably come across him and Chabauty-Kim. If you're listening in South Korea, you will probably know him as well, as he's the author of numerous very popular books on mathematics in South Korea, and we talk a little bit about that. And I caught up with him just after our conversation, and he is maybe about to pull the trigger on getting a translation out here in English in the UK and elsewhere. So hopefully that happens. But this is someone who you should listen to. He is a very accomplished mathematician, as I said. So we talk about many things. We talk about how mathematics should connect to the world. We talk about how many people see physics perhaps as drawing on mathematics, but it can go the other way, and not just in the famous example of string theory, but again in Professor Kim's own work, he has drawn inspiration and ideas from physics and used them in number theory. At the very end of the conversation, we end up discussing whether mathematics will ever end. And I want to add just a little note on that here, because I reflected on this a little kind of further after the conversation. So I hope this isn't a spoiler, but I feel like as long as there are problems to be solved, as long as we're inquiring about the world, math will be part of that. I'm James Robinson. This is Multiverses. I hope you enjoy this conversation. Minhyong Kim, welcome to Multiverses, and thank you for hosting me here at the International Centre for Mathematical Sciences on this beautiful, unusually sunny day.
Well, no, thank you for your interest. I'm very happy to be interviewed and to have a chance to talk with you.
I'm hoping today that we'll talk about different ways that mathematics intersects with other subjects and with human life more generally.
Right.
But perhaps we can start just by saying, what is this thing, mathematics? You have a few lovely quotes on your website, but do you have a favorite perspective on what mathematics is?
No, in some sense. That's maybe that was part of the point of the quotes I put on my website. Many people say many different things that cast light on different aspects of mathematics. But the point is that it's hard to say what anything is. Right? So if you ask me what mathematics is, you might expect some kind of a concise answer. But suppose I ask you what even a cat is. That's very hard to answer, right? And this is an old philosophical problem to say exactly what we mean by a cat. But if you move into the realm of, say, scholarly matters or culture or something like that, suppose I ask what literature is.
Yes.
Can you give a concise answer to that question?
Not easily, not a kind of analytic answer as the philosophers would like.
Right.
I guess it's, you know it when you see it, maybe?
You know it when you see it, then you answer by some complicated procedure of delineating boundaries in some way, but none of the boundaries are even very clear-cut, right? So if somebody asks, well, is mathematics literature? After all, it's written text, and you do a lot of things, and some of it has something of a literary flavor. Other things seem more dry and so forth, right? So, what mathematics counts as literature and what doesn't? It's a pretty hard question to answer, right? So, I think it's the same with mathematics. What exactly counts as mathematics is very difficult, but I do like to point out, or at least call attention to some misleading characterizations of mathematics that exist out there, here and there, especially among people who regard themselves as intellectual in some way, right? So one idea that was very popular through a fair amount of the 20th century that's still with us is that mathematics is logic. Mm-hmm. It's just logic. The process of deducing B from A, right? You start from some assumption A and deduce some assumptions B. And I do like to point out that this is a very, very misleading characterization of mathematics for a number of different reasons. The first obvious reason is that a lot of people use logic, not just mathematicians, right? Anybody who does anything scholarly certainly needs to use logic to carry out their argumentation. Physicists certainly use logic all the time. They use mathematics all the time as well. And even in ordinary life, we talk about certain modes of deduction being reasonable and things not. We think that some argumentation is okay, some modes of arguing that doesn't seem correct, and so forth. So it's part of everyday life, the usage of logic, and the way mathematicians use it is really no different from that. It's the only difference is kind of a quantitative difference, because we tend to be more fussy about it, and we tend to make it more explicit. We tend to create more noise about something being correct or not, right? But the way mathematicians employ logic is the way anybody else does. It's just create convincing arguments, right? So that's one way in which mathematics is not logic. Everybody uses logic, not just mathematicians, right? And the other, of course, is that this mode of convincing arguments, convincing argumentation is just a part of mathematics. There's a lot of other parts of it that involve discovery, experimentation, calculations, philosophical speculations, building of theories, and so forth. And there's so much of mathematics that doesn't involve exactly this process of correct argumentation. Right? And in fact, there's enormous amount of preparation before people arrive at a logical argument to convince somebody else that some theorem, let's say, is true, right? So that's all being left out with the characterization that mathematics is logic. So those kind of things I like to point out. That mathematics is certainly not logic. Now, I'm somewhat more favorable to the idea that mathematics is a kind of physics. In the sense that it seems to try to figure out, it seems to study properties of some very fundamental aspects of the world, right? And some of it which directly overlaps with physics, like if somebody tells you the volume of a sphere or something, right, which is supposed to have been figured out by Archimedes, that's of course a statement of physics as well. It tells you how much water can fit inside this ball and so on, right? So there are direct overlaps, but even where the overlaps are not so direct, it does seem like it's investigating features of the world that are very, very basic and fundamental to the way reality is made up. So there is some way in which it is closer to physics probably than logic. And then you probably know, you know this cosmologist Max Tegmark.
Yes.
Right? And he has this idea that the universe is nothing but mathematics, right? And I don't think I quite agree, but I kind of see where he comes from. It's because there are lots. I don't know. The physicists believe that the whole world is made out of elementary particles, for example, right? And it's hard to say what elementary particles are, except as a mathematical object.
Yes. Yeah.
Right. And the way you build more complicated things up out of these very elementary things is also a very mathematical construction. So that's, I think, the inspiration for this idea that the universe is just mathematics, right? So from that point of view, maybe that's what mathematics is. It's just the structure of the universe. So all these different perspectives are possible. But as I said at the beginning, saying what anything is a very difficult task.
It's a dangerous task.
I'm not going to do it about mathematics. But by the way, it's sort of related, you know, in a vein that's somewhat related to this idea that mathematics is logic, right? I think there are people who expect there to be a clear-cut answer to the question, what is mathematics? And I do wonder where this expectation comes from, right? But maybe it comes from the fact that in school mathematics tends to have clear-cut answers. You pose problems to people and there's supposed to be some correct answer, right? And if you're used to that mode of working with mathematics, maybe you expect even about mathematics itself to get a clear-cut answer.
I mean, many thoughts strike me. As you say, maths is introduced as this very certain subject in school. Right. But I do sometimes wonder if, in the long run, it will be the undecidability part of maths that will sustain it for longest, in that it will never be completed, perhaps. I was also struck by the first quote that you have on your website is the Vladimir Arnold famous quote saying, you know, math is just the part of physics where experiments are cheap.
That's right.
But I do wonder about that if the hierarchy is correct there, or indeed is the relationship not so much a hierarchy as some kind of symbiosis. Perhaps, there's a continuum between the concerns, I think, of maths and physics, rather than one being subsumed by the other.
I think there's a continuum interpolating all aspects of human knowledge. Right? It's not just mathematics and physics. So that's one thing. But also, I think we need to distinguish a little bit here mathematics or physics as subjects, or sort of disciplines or areas of study, and the objects that they study.
Yes.
And sometimes these two questions tend to get conflated when we discuss matters of this sort. So as subjects of study, there's certainly a continuum and there's a reliance on each other. But it's probably also true about the objects of study.
Yes. Another thing I've seen you point out about the way that maths is represented, which is perhaps problematic, is that it is described as this very detached thing, almost otherworldly, I think you've noted sometimes. Perhaps partly philosophers are to blame for that. But one of your roles is the director for the Centre for Mathematics for Humanity.
That's right, yeah.
And so it seems clear that you're trying to ensure that mathematics is more connected to broader human concerns. Perhaps you can speak a little bit about the way that you think maths is represented, or about the Centre's work.
Right. Well, of course, as a mathematician, part of me wants to believe that all of mathematics benefits humanity.
Yes.
But it's still possible to talk about some benefits that are direct and some benefits that are much more circuitous, right? And so we do believe that there's a kind of grand network of knowledge in mathematics, which is coherently connected to each other, and some of it directly touches on matters of human concern. And so our Mathematics for Humanity project tries to support these kind of things rather directly, again, by providing funding to mathematicians who work on problems like climate change, problems like sustainable energy, sustainable economics, healthcare. So we've provided funding to mathematicians who work on these things, and especially money for funding and other kinds of resources for people to gather here to have meetings on this subject, to share ideas and try to bring about progress on these very important challenges that face humanity. So that's largely what Mathematics for Humanity is about. There's also part that has to do with sharing mathematical resources with the developing world. which is of course very, very important in the current situation. I mean, I was just discussing something this just now with a mathematician who was at our workshop this week, that it doesn't seem to be very well known that according to various estimates, for example, from the World Economic Forum, within probably 10 years or so, more than 50% of the young people in the world are going to be living in Africa. Right? So to think that it's not our concern is a grand illusion, right? So if you might also be one of these people who think that Africans can be confined to Africa. This is a ridiculous idea. I think everybody knows, most people acknowledge this, but also building up educational infrastructure in different parts of Africa is humanity's concern. Right? So that's another part of our Mathematics for Humanity program, for Africa or other parts of the world where somehow we need more collaboration with parts of the world where we have more mathematical resources. So we are supporting meetings and training sessions and things of this sort in many parts of the world through the Mathematics for Humanity program. So this is a kind of a brief view of what we are doing, but as I said, it's probably trying to call attention to those parts of mathematics that touch on human welfare in a much more direct way than, say, number theory or particle physics.
Right, yeah. I mean, I think it's fair to say that some branches or some disciplines have really co-opted mathematics, like physics we mentioned, but obviously economics as well.
Right, of course, yeah.
But perhaps then there are other places, as you mentioned, where there ought to be more mathematics, or mathematics can be a very valuable tool. Is there any field in particular? I mean, I feel that climate science is becoming, or is pretty mathematical already, but are there certain places where you feel this needs more?
I'm not well positioned to really judge where the priorities are at the moment, but I can tell you there are lots of mathematicians already working on a whole range of things that are of the benefit to human welfare. Among the projects that we supported was somebody at the University of Edinburgh who's developing efficient batteries, for example. This is a very important problem. We've supported a project called Rewilding Mathematics, where you try to bring together people in mathematics and ecology to figure out the optimal ways of rewilding parts of the country where there's been a lot of environmental degradation. So things of this sort, all of these are important. So I'm loath to say that this is more important than another, right? But there's lots of it. A lot of it is already going on. But I feel like the announcement of our project, especially with a slightly pretentious name like Mathematics for Humanity, did create some energy. So for one thing, it provided not just funding but also attention to people who are working on these vital problems, right? And also gave a certain sense of synergy and coherence to the different kind of people who are doing such things. So even without me saying that we are going to support X, Y, and Z as high priority, I think that can be decided by the community, and our job here is to respond to the community needs.
Right, yeah. Yeah, I think, as you say, just raising the point or making it more salient that mathematics should be serving human concerns is a valuable endeavor in itself. I think the other piece that you mentioned about education is interesting too. I'm thinking, there's a quote from one of Harari's book, I think something like, the algorithm is the most important concept in the world right now. And it strikes me that mathematics is, in a sense, becoming more and more important within society in a way that perhaps physics is not. Our physical world is not really changing. Okay, we have faster cars, but we're not living at relativistic speeds. But to a greater extent, our lives are being intermediated by algorithms. And I wonder, I don't know, but I wonder, is it important for that reason that people have greater mathematical literacy? Or do the details of algorithms perhaps not matter?
It's a very difficult question, and it's an interesting question. It is a question I think about quite a bit, right? It's sort of like driving a car, right? Many people know how to drive a car. Very few people know how to fix a car when it breaks down, right? And it's probably not that important for most people to know how to fix a car, right? On the other hand, if you do know how to fix it, it's a great sense of empowerment that you get compared to just feeling helpless when your car breaks down, right? So that's a kind of analogy one can draw. But I don't think that's quite the right analogy, exactly because of what you said. Mathematics does tend to be more abstract than physics. That's a sense that many people have. The abstraction is for a reason, of course, and this is well understood by many people. It's because sometimes when you abstract certain structures out of a specific problem, it turns out that what you study or the theory you develop is much more broadly applicable than the problem that you started out with. And so that's where abstraction comes about. But as a result, it does seem to, even though I also pointed to the close relation between mathematics and physics, it does eventually seem to become more broadly applicable than ideas of physics, especially with the information revolution. So much of information is concerned with mathematical tools and concepts, and as we know, there's advanced number number theory contained in each of our smartphones, right? So all of these things are astounding somewhat, and it happened in my lifetime, of course, this incorporation with quite abstract mathematics into technology. And so returning to the education question, I'm tending to digress, but of course, anybody can decide that they only need X amount of mathematics, right? So you learn mathematics in primary school, secondary school, and so on, and most people wouldn't go on to study it at the university. So you do have to decide how much you need, like in the case of a car, right? How much do I really need to know about a car in order for it to help my life, right? On the other hand, you also strictly speaking, you don't have to know how to read to get by in life. You can probably figure out various survival strategies to know how to read. On the other hand, in our modern world right now, if you didn't know how to read, your life would be very, very restricted, right, by this inability, right? So that's the decision one needs to make. So, sorry about that. That's a periodic fire alarm test.
I guess 11:30 on the dot.
That's right. Yeah. Yeah. So try to answer your question. I can't really say for any individual how much mathematics that they will need, right? But we do seem to be living in an environment, the more you know, the more empowered you become, the more options are open to you. And to some extent, everybody knows this. Almost any kind of workplace you go to these days, if you know math, it does tend to give you an advantage in some way. Anything in the technology direction, for example, or information direction, or even if you're a journalist, because of all the science news that's coming out, if you have some understanding of math, it seems to help broaden your options, the kind of things you can do. So the more math you learn, the more empowerment it provides. I think this is a reasonable statement. But how much a given individual needs, they have to decide. So as somebody working in an educational institution, I think the best we can do is, as accurately as we can, equip people with an understanding so they can make good decisions. And I don't know if this is an answer to the question you were asking. But.
No, I think that's a good answer, and I think that's very clear. I wonder also whether the arguments that we'll need to give for studying mathematics or any subject are going to have to evolve. We may be, again, it's very uncertain, but we may be on the doorstep of a future where the economic value of studying something is very marginal.
Sure.
So it may come down more to the things you alluded to in terms of how empowered you are, how does learning this help you flourish? And I wonder if, in fact, maybe maths may be in a stronger position in such a future or a weaker one. I think there's certainly some subjects which people just won't make much sense to study, and the arguments will be around passion and human flourish.
Right.
I'm curious, do you think mathematics could become more prominent if we do move into a kind of future of abundance?
Yeah, no, it's of course very hard to predict. Compared to many people, by the way, I'm quite a fan of the new technologies that are coming about, and it's very exciting. So, for example, I learn about lots of things using ChatGPT these days, right? Especially because I work at the interface of physics quite a bit, and physics language is sometimes hard to understand for mathematicians. Sometimes I ask ChatGPT, what is this person talking about? It's often very helpful. So I'm a great fan of using whatever you can to learn new things, whatever is available. Whether mathematics will become more important or redundant as a result of this is very hard to predict. But one thing that did happen in my lifetime, I can share, which is when calculators were becoming very widely distributed, right? Similar questions came up at that time, not exactly the same questions, right? But people did ask, do we really need to learn, say, mathematics in school when everything can be done with a calculator? And as far as I can see, so this discussion was happening, say, already in the 1980s, about 40 years ago, right? And there was a lot of concern. Now, what has happened in the meanwhile is calculators, or more generally computational tools, have been incorporated to mathematics education. Nowadays, you get the computational tools makes it so much more interesting to teach different kinds of mathematics. You can see it on the internet, the various YouTube instructional videos and so forth. People use technology to enhance the learning experience incredibly, right? And using some kind of scientific computation in mathematical research is also very common, not just in education. And during the last 40 years, since these issues were first discussed, the need for mathematics in the meanwhile has become more intense, not less. So I don't know if that's sort of that helps us predict the future or not, but that is something that I've experienced in my lifetime.
Yeah, it's interesting. I think we can probably see calculators have been some kind of cognitive prosthetic that have allowed us to, possibly it means that less time needs to be spent on, how do you add and
exactly,
and you can actually get to the more abstract areas or explore more mathematics in the same amount of time.
A large amount of by the way, within what people sometimes think of as pure mathematics, a lot of the interesting development is computation with very abstract objects. If you have abstract input and abstract output, how do you compute such things? That's been an enormous industry that my research itself has benefited from, for example. I think what you're alluding to is this phenomenon that when a new tool shows up, right, people have a tendency to try to do not much more than they used to once you have this tool at your disposal, right? So from that point of view, maybe mathematics will become more intense because simply mathematicians will be trying to do much more than before.
Yeah. The other thing I'm reminded of, I don't know if you've read the story I think it's called That Feeling of Power by Isaac Asimov, and it's about this. He must have written it around the time when calculators were.
I don't think I've read it.
It's a wonderful story. It's just one of his short stories. Right. But it's when I think he wrote it when calculators were becoming more common, and it projects kind of a far off future where no one knows how to add or do algebra themselves, essentially, or arithmetic themselves. But there's this one guy who kind of reverse engineers it. He figures it out, and it's I can't remember why, but he ends up being incredibly necessary for the survival of their civilization. But I think the title of the book or the story is very interesting. Just that it's called That Feeling of Power, and it's it says, well, even if suggests. Even if we don't need this, although I think the twist is they end up needing it, it's just that sense that I'm able to understand what's going on here, and I can prove it because I can do the calculations.
Sure. Yes, and the need is itself a very complicated thing, right? What do we mean by we need X, let's say? So, well, I can, again, maybe just to mention some of my experience. I told you a moment ago that I learn things using ChatGPT, for example, right? But I do feel like if I use it too much, it feels a little bit uneasy. So then, after getting general guidance, I do need to go back and do my own work to try to figure out, give some more substance to what the machine told me. So that might be related to the kind of experience you're describing in that Asimov described in the story.
I think that's right. I don't think there's any... there's no sort of matrix scenario where you can just wire knowledge into your brain. I think it is just intrinsically hard learning something new, and it's sort of, to use that word again, perhaps needs to be hard.
Right. Yeah, well, that's related to this kind of software-hardware problem, right? That even when you think that you're going to just plug knowledge into your brain, that's a kind of pure information viewpoint on what knowledge what constitutes knowledge, right? Whereas in any of our human experience of it, there seems to be a very important hardware component that somehow the process of acquiring it in a certain way seems to be part of the knowledge we have. And that can't be just reduced to the information that was injected.
Yes, yeah. I'm also, again, the word need is prominent in my mind, but I should mention that, I mean, many people will know this, but others may not realize that you're a best-selling author in Korea, and I think your breakthrough book was The Moment That You Need Mathematics.
That's right, yeah.
And as I understand it, it not only was a huge bestseller, but it almost introduced popular mathematics as a sort of subject in the book scene in Korea. So I wonder if you could just say a little bit about that journey. What made you want to popularize mathematics, and maybe you can give like a very brief description of that book. What was the hook, I guess?
Right. It was kind of an accident, actually, the book itself. Communicating mathematics is something I've always liked to do, as long as I can remember anyway. And then I started doing it rather intensively around 15 years ago, actually. It's not that long where I started seriously engaging with the public through public lectures, appearance on various YouTube channels or TV programs and so on. But then at some point, a publisher contacted me with this idea for the book. And what they suggested is that I should give to their editors a series of lectures. Right? And then the editors would ask questions, I would respond to that question, and we would discuss it, and let's turn that discussion into a book. That was their suggestion. And it worked quite well. So, the editors put in a lot of effort, of course, to clarify whatever, to make clear for themselves and therefore for the reader what I was saying. And so I owe a lot to them. But somehow this book seems to have struck a chord. And this is tooting my own horn, but I have been told what you said a moment ago, that somehow it started a boom for popular mathematics books in Korea. And it was within the I think at its highest rating, it reached the top 10 in the general books bestseller list for a period. So, but exactly how it came about and what made it into such a popular publication, I really don't know. It was these things seem to just happen on their own.
Yeah.
But the nature of the book, by the way, is something I don't think it would be very popular in the English language. I did realize after writing this book and after various translations were attempted and so forth, that popularization of mathematics it does also carry a lot of cultural baggage. You do tend to rely on things that a specific readership you have in mind is likely to respond to and so forth. So I have this an English version, which in fact right now I'm discussing with a publisher whether we should put it out right now? Well, actually, I have to decide at the moment because it will involve quite a bit of work to make it palatable to the English reading public, I think. So, but part of the reason is exactly this. It does take work. I realize that I need to tailor it somewhat more to the readership here or in America in order to make it into a successful book. But it was an interesting experience realizing these things, how much I had written it for the Korean readership.
Yeah, I mean, again, like, as we said, math is obviously, or so often portrayed as very detached.
Right.
You would think, well, you can just package this up and it will sell to everyone, it will make sense. But I guess is the difficulty the way that you connect it to things that people know about and understand?
Things that people can relate to.
Right.
That's one way of putting it. I think there were many such things, but two ingredients that stood out as I was considering this challenge and problem was, firstly, it's true that the Korean readership has more tolerance for equations. So you probably know this Stephen Hawking quote where he says that with his famous bestseller, each equation was supposed to cut the sales by half or tenfold or whatever, right?
Yeah.
So his publisher warned him about that, and so eventually he only put in E equals MC squared or something, right? So the Korean public does have more tolerance for equations, for mathematical formulas appearing inside books. So that was one sort of obvious thing. But another aspect, which might have been harder to predict, is that they do have more. I found that they have more tolerance for philosophical digressions. So when you sort of try to get at philosophical motivations for thinking about some aspect of mathematics, Korean readers and audiences during lectures seem rather like this. What I found what I found in the UK is that during lectures, when you're face to face with people like philosophical insights or motivations. But when it's written down, it doesn't go over so well. That's my impression here. So somehow, maybe part of the reason is that people find mathematics so painful anyways that going into the philosophy of it makes it even heavier, the experience. So I don't know what it is, but these were the kind of standout features that seem to be somewhat culture specific when I consider this problem of translation.
Yeah, that's interesting. I wonder about that. I've heard that equation quote before. I couldn't remember it myself precisely, but I just wonder how well tested that is.
No, I know. That one needs to challenge it, of course. I agree. But the publishers are wary. That's that's
the gatekeeper effect. And it does surprise me as well that physics, I think, has become very popular. There are popular maths podcasts and there are popular maths writers in English, but I just don't think they command the same sort of share of audience as popular physics. And yet the popular physics does touch a lot on philosophical issues. In fact, I think that's why people buy popular physics books.
That's a very good point. Yeah, and I exactly thought about this question as well, right? But reasons again for anything are very hard to understand. But that's why I'm somewhat leaning towards the explanation I gave, the second explanation in some sense, that when it comes to mathematics, people would like a light touch because it's regarded as such a painful subject anyway. Whereas physics, of course, if you get to the inside of physics, as you know, it just involves enormous amount of mathematics, right? But that's not the conception people have from the outside. In fact, many people are highly surprised, very, very surprised when you show people how much mathematics there is in the actual research papers. They don't quite realize that that's the way research in physics is done. So somehow physicists, the public image of physics is very different, although on the inside maybe it's not so different from mathematics.
Yeah. This might be a good moment to bring up your own work. We've mentioned number theory a couple of times, just as an example of something that's completely disconnected, or perhaps the most disconnected part of mathematics from the world. And yet, Gauss famously said, maths is the queen of the sciences, and number theory is the queen of maths.
Right.
And you are a number theorist, and yet your work, as I understand it, does perhaps unusually draw on physics in a sense, whereas often we see the reverse. We see physics drawing on maths. You've sort of put your head above the parapet and said, mathematicians can take something from physics at some level. Perhaps you could tell us a little bit about what your work is and how it's drawn on physics.
Maybe let me comment on the first part of your statement briefly first. At the moment, number theory is probably the most applicable part of mathematics. It's hard to quantify such things, so I'm just making an intuitive statement here. But this again is something that happened in my lifetime, and it's mostly because of two things: public key cryptography, that's one thing, and the other is information theory, mostly coding theory. So in order to make efficient codes that can correct errors automatically, you use quite a lot of number theory. and the cryptography part is also important, where you can exchange information securely, even with publicly known codes. This is kind of the tricky part of public key cryptography. And as I understand it, each of our smartphones contain something called elliptic curve code, right? Which is a very number theoretic object. And you do all of these things. You work with all of these things over something called a finite number system, or finite field. That's what it's called, a number system with only finitely many numbers in it. So these are all very highly abstract things. But from a kind of technological viewpoint, it's probably among the most applicable areas of mathematics at the moment. It's quite surprising. So when I was working in the U.S., I used to teach a postgraduate course on algebra at regular intervals, and I was amazed that over the years there were more and more engineers in my course, and basically they wanted to learn about these kind of structures.
Yeah, so. I guess it's also not something that's just being left alone, because they're still trying to prepare for a quantum future where
Indeed, that's right.
You can factorize things much quicker. So,
exactly. And you probably heard about this, but the early proposals for post-quantum crypto systems also involved elliptic curves.
I was surprised that essentially we can use we can rely on the same kind of concepts. We just need to go a bit further, although there's other approaches as well. But
that's right. I mean, there are a number of different approaches, but I was quite fascinated at the time that you took it again up to a slightly higher level of abstraction. You consider not just single elliptic curves, but something called the isogeny graph of elliptic curves, or a whole collection of such things that taken together, it was hoped that they would provide a crypto system that was secure against quantum attack. So anyway, so number theory is very much in the thick of things right now when it comes to how to use mathematics to create new tools or make the world secure or things like that. So that's one thing. And it might not be unrelated to the second part of your question, the relation with physics. So firstly, in my view, this interaction has been two ways for quite a long time. It's not nothing new. It's just that the degree of consciousness of how much traffic is going one way or the other, it might be the only thing that really changes as far as people's practice is concerned. So much of mathematics is developed in relation to physics. This is a bit of a digression, but as a digression I find a bit interesting. So, I think it does provide some illumination on this question. People often talk about this unreasonable effectiveness of mathematics in the natural sciences, right? That's this famous paper of Wigner. And there's also a famous quote by a mathematician named Gelfand on the unreasonable ineffectiveness of mathematics in biology. That's been quoted often as well, and as a kind of strange phenomenon. Whenever people try to use mathematics in biology, it doesn't go very far. Now, of course, this is an exaggeration because it all depends on what you mean by mathematics and what you mean by biology, right? So, for example, everybody uses data science and information theory and statistics in biology, and this is actually very advanced mathematics by the standards of, say, even 100 years ago, right? So if you regard that, but of course it's so well understood that it's regarded as kind of elementary mathematics right now, but within the scheme of history, it's very advanced mathematics. So from that point of view, already you're using a lot of advanced mathematics for biology. But what Gelfand meant is that if you take some of the current tools of mathematics, like algebraic geometry, topology, things of that sort, they seem to have surprising applications to, say, string theory or quantum field theory, things like that. But you can't get this kind of very structurally sophisticated, what's now regarded as structurally sophisticated mathematics to feed into biology.
Yeah, I had, I don't know if you know his work, but Geoffrey West, who was a physicist,
right.
and he was actually the director at the Santa Fe Institute of Complexity for many years, but he sort of later in his career, he turned to biology and looked at scaling laws and managed to apply, lots of mathematics around fractals and topology to figure out why it is that, our blood systems and trees all kind of branch in the same way, and the implications that has on metabolism. So it's really interesting, and he sort of managed to derive particular scaling laws, for example, that as an animal doubles in size, its metabolic input only needs to increase by 75%. And the same is true of trees, and the same is true of pretty much any animal, which is, as you go from an organism of one size to another, that happens. But yeah, it's sort of, his work is kind of the exception.
I don't think it's quite an exception. So let me give you a slightly different perspective on that, which is that I find it very, very interesting, those kind of things. And that's not the only thing. Of course, there are people who find scaling laws in economics, organization of society, all those things that they do at Santa Fe are concerned with such things, right? But to some extent, Gelfand was really pointing to the fact that for most biologists, maybe even 99% of biologists, this is irrelevant.
Yeah.
And I think that's a fair assessment. That people may say, oh, that's kind of interesting, but whether it really does something for their research, it's a very, very small portion of the population who would agree to such a thing. Whereas in physics, almost all people working in, say, quantum field theory, which everybody regards as an important area of physics, right? Thinks they should know more about topology, geometry, algebra, and so on. So it is a striking difference, even if you take that kind of research into account, the way it's incorporated into the community consciousness.
Yeah. I do sometimes wonder with Wigner's quote is if actually it shouldn't be so surprising that mathematics is so effective, because at least, physics presumes a fairly well-ordered world, one where you can write down some laws which always hold and describe things with precision. And I almost can't imagine any kind of physics, anything that conforms to that very loose description, that in a sense would not be mathematical, in that maths would not be your best tool for describing it. And so, to me, it perhaps doesn't seem so surprising that if you're studying something that's ordered, just by focusing on the ways that things can be ordered and the structure of things in the abstract, you can find concepts which actually do occur in the real world.
Right. So, as I mentioned earlier, and as you know, it largely does have to do with what we mean by mathematics, among other things. So that's why I started out saying that even in biology, of course, there's a lot of mathematics that's useful, right? And that's related to another quote I put on my webpage. You remember that there's this quote from David Gale and Lloyd Shapley, the economists, right? And their view was that any kind of thinking, once you make it precise enough, becomes mathematical. That's kind of their characterization of what mathematical methodology is like. And I tend to sympathize with that view as well. So also from that point of view, then of course physics is going to be mathematical. Of course biology is also going to be mathematical, the more people try to make it precise, right? So when Wigner was saying things like that, I think he was thinking, I think he was, okay, it's been a long time since I read that essay, so I'm a little bit reluctant to try to guess at his intention. But my suspicion is he was thinking about specific kinds of mathematics.
Yeah.
So for example, group theory. Group theory was an enormous thing in quantum mechanics during Wigner's lifetime, to which there was a lot of resistance, as you'll recall, among physicists, right? People spoke about the disease of group theory and didn't like to admit that this would be relevant for physics. But somehow it became a very important thing, not just in quantum mechanics, also in special relativity. People soon realized that this study of the Lorentz group was essential to understanding how relativity works, and especially essential to understanding how it combines with quantum mechanics to give you quantum field theory. So group theory started making its way into physics in a very, very serious way in the course of Wigner's life, in fact, and I have a feeling he was thinking about this kind of mathematics. It doesn't seem to be the kind of mathematics that just comes out of precise thinking in the way, say, data science or statistics or probability theory even might come out of trying to make your ideas precise, but still somehow it's enormously powerful. So my suspicion is these are the ideas that were going through his mind. So it's not as though, so in other words, if you talk about the ineffectiveness or effectiveness of mathematics, mathematics involves so many different things, it's hard to know exactly what we mean.
Yes.
But so we will probably do need to focus on specific conceptual tools, like you might say, why is group theory so useful? Why is group representations, or why is functional analysis useful? And then the questions become more precise, and more of the mystery that he was struggling with probably does emerge when you ask these more precise questions.
Yes, that makes sense. Yeah.
I don't think I answered the original question.
No, we went on a really interesting tangent. I think my original question was, tell us about your own work and how.
Yeah, well, you see, I don't like talking about my own work. It doesn't seem so interesting somehow.
That's fine. We can refer people.
But maybe I will say one thing in relation to quantum mechanics, right? Because that is what I'm trying to use in a lot of the number theory that I'm doing. And it might be of a number of reasons. Again, it could just be that the ideas of quantum mechanics are also just basic things. It arises in the context of quantum mechanics, but it could be that the structures are just as basic as addition and multiplication, so you expect to see the similar kinds of ideas and concepts arising in other contexts. So that's one possibility. But my more speculative hope, or pipe dream, you might say, is that number theory tends to, especially what I do, something called arithmetic geometry. That's the study of geometry over small number systems, like the integers, or integers with a few more numbers thrown in, or even finite number systems, right? This is quite different from what the number systems people usually use to describe geometry, which is like real numbers or complex numbers. Right? So the arithmetic geometry is geometry over a small number system. But the number systems that you study in arithmetic geometry, that you use in arithmetic geometry, are number systems that have an intrinsic discreteness. So in particular, the geometric objects of study, the functions defined on these geometric objects are also discrete intrinsically. Right? So I feel like this is something that should be useful for quantum mechanics. So everybody knows that there should be, in this idea of, say, the hope to get some kind of a quantum gravity, right? You need to describe, you need to combine this geometric nature of gravity with the discrete nature of quantum systems in some way. Right? And you can't imagine a coherent geometry that combines with discreteness, but a version of it already exists. Whether it's relevant to physics or not, of course, as I said, that's just a pipe dream. but a version of a coherent geometry using discrete number system already exists. This is arithmetic geometry. That's the research that I started from. So from that point of view, maybe connections are also natural.
Yeah. Yes, that makes sense. I think, I mean, as you say, if we have one way of describing one system for describing discrete systems, then it might just apply in all sorts of places. I'm reminded of, there's this quote from Poincaré, which is, maths is the art of giving the same name to different things. And I think physics is very similar. Like they're both so looking for that same kind of unity,
Right.
where you might, in physics, you can call it a gravitational field, or you can say that actually you're just accelerating in space, right?
Sure. Well, the idea of a field, by the way, is a very interesting example. So of course, I think it arose in physics. It's hard to say about any of these things, but nonetheless, of course, that turned out to be just a general purpose tool.
Yeah. I do have to say, I'm not sure if the jury is out on whether the world is discrete or continuous. In that, the quantum field theory is a theory on fields. They're very continuous things, but then you get this quantizations of the field. So yeah, maybe there's a kind of discreteness that I know emerges from the continuum, as it were. But
or the other way around. So starting from the classical fields could be misleading. That's a viewpoint that many people have as well. In my view, that's a more consistent. I don't know what the reality is, but that is a more consistent view, I think, than starting from the continuous and moving to the discrete.
Yeah, I think many people have speculated on this. Leibniz said nature does not make leaps. I don't know if you know that one. And then you probably know the David Mumford quote where he said minds are discrete, but nature is continuous.
I don't know.
But no one really knows. I mean, it could be that minds are continuous and nature is discrete if you're a dualist, but that's probably unlikely.
Well, all of these are difficult concepts, of course.
Yeah. We've talked a lot about how useful mathematics can be. I do wonder if, though, there are places where we over-rely on mathematics. I'm thinking again of, I'm thinking in particular of, I think it was Krugman who said, what did he say? Something like, we sometimes mistake truth, or sorry, we sometimes mistake beauty for truth when it's, clad in the impressive robes of mathematics. And then on the physics side, Sabine Hossenfelder has been arguing physicists have been seduced by mathematics, to the extent which, say, they're relying on aesthetics too much. Do any of these resonate, or do you think we can never go too far with mathematics?
I fear that I'm not going to be answering your question again, but let me pick on both of those quotes maybe simultaneously. Right? Maybe I'll pick on Krugman first because that somehow is easier to pick. I sympathize with what he's saying to some extent, except to think that mathematics is about beauty is a very narrow view. So, and I guess this applies to Hossenfelder as well. The idea that you might be misled by the beauty of a model, I'm sure this can happen, right? But it's not the same thing as being misled by mathematics. Some beautiful model may be couched in mathematical terms, right? But for a mathematician as well, when you're trying to develop mathematics to understand a phenomenon, right? A lot of it is often very, very messy, and you have to live with that messiness. Now, sometimes after a few hundred years, or sometimes 1,000 years, the messy mathematics gets cleaned up to something more elegant and beautiful. But to think that mathematical models themselves are supposed to be beautiful, this is itself an extremely narrow view. So from that point of view, I somewhat reject the beginning of their sentiment, or even while accepting aspect of it, the idea that people can be misled by the beauty of a model. Of course, it can happen, right? But that's not being the same as being misled by mathematics. Returning to a subject that we've already touched on, if you take something like quantum field theory, most of it is not beautiful at all at the moment. In fact, it's a major challenge how to make it properly consistent mathematically, right? And I think you can take aesthetic sensibilities too far. I agree with this, but I don't think this is the same as taking mathematics too far. This isn't answering the question of whether mathematics can be taken too far or not, but that's a kind of an answer to your question. So maybe I will answer this question of whether you can take mathematics too far. So the question, there are again many different aspects to mathematics, right? Suppose we go back to this characterization of Gale and Shapley, that mathematics is just precise thinking, right? Can we take precise thinking too far? That's another version of the question, right?
Well, I think sometimes we are tempted to make things more exact than we can. I mean, this is Aristotle's thing, like you do not admit into your science more exactitude than it truly permits. And I think certainly in economics, there's this perhaps desire to cut through all the noise and get to an equation, but actually, that's we don't have the, I don't know, we don't have the quantity of data, or we don't have or even just as humans, we don't have the predictability that you need in order to, completely apply mathematics. There has to be an element of, I don't know, vagueness.
Yeah, the economics, of course, is a very complicated case in some way. So I've had a lot of conversations with economists about their mathematical models. So, for example, economics has many famous theorems, right? Like even the existence of a Nash equilibrium, this Gale-Shapley algorithm that I referred to a moment ago, Arrow's impossibility theorem, and so forth. So I have asked economists, are these really useful? And the subject is, economics is also changing very rapidly, of course. Many people are conscious of the idea that to get really useful economics, you have to deal with much more messy collections of data, right? And this is being taken on board, I think, by the more serious economists right now. But even the older, very mathematical economics that you look at, the theorems I was referring to, I think their view is that they may not be directly useful, but they do give some insight on real phenomena. And that's why they like them. So I forgot what your question was.
I know. Your questions aren't really so important as if the answers are interesting, which they are. It doesn't really matter if they are.
Yeah. So one economist I know relatively well is somebody named Ariel Rubinstein, and he likes to say economics is a story. And I think he means two things by this, and I've checked this with him, and he neither agrees nor denies, but my impression is that he agrees. When you say economics is a story, right? On the one hand, he is acknowledging that you can't make precise predictions, of course, right? It's not about making, most of economics anyways, even though, again, that's changing, but most of classical economics, you can't make precise predictions. It's not like experimental science or something. Even though even experimental science is not like experimental science. But anyways, that's a different story. But anyways, so he says economics is a story to express a certain degree of humility about what it's able to do. But I think he also means that it is like a story in the insight it gives. So when we think about great literature, and he says Chekhov is among his favorite authors, right? When we think about great literature, again, it's not experimental science, but it gives us we can't avoid the feeling that it gives us a deep understanding about the way the world is put together. That is what great literature does for us, right? And I think he's saying that economics can do this as well, in a different mode from literature, but still in the same sense of providing insight. So I tend to agree with him about economics in this way, and about a lot of usage of mathematics in different realms of human knowledge. That there are at least these two different aspects. making precise predictions, making things very, very precise. The other is giving global insight of some sort.
So maths is a story as well, a way of...
So I gave a lecture called What Kind of Story is Mathematics? I don't know if you've seen this, but I can send you a link.
I have, so I've cheated.
Right, oh, I see, yeah.
So I knew your answer to that.
Right.
I think one of the really interesting points you made in that is maths is a kind of continuous story.
That's right, yeah.
And it's actually very collective. It's a lot of people writing it together and reading it together. I hadn't realised how collective the reading of maths was, but you point out that. One thing the question that I was left with after watching that was, is it a story that will ever end? It's in the moment, it just seems like it's, one chapter after another, and it's just gonna. But do you think there will be a place where I feel with physics, we assume that it is, we'll get to some final equation, and that will be the end of what there is to be said. I may be wrong here, but I feel like there's a assumption on many people's parts that once you get to the theory of everything, you're just going to be doing, figuring out how everything else derives from that. But is maths more open than that, do you think? Or will we sort of get to a point where we've said everything novel that can be said?
I don't see how it could end. Let's put it that way. It seems to go on and on. By the way, even in the case of physics, people talk about theory of everything as a kind of propaganda device.
Yes.
But I don't think anybody really believes.
Yeah, I don't think they'll say, okay, well, we're out of the job now. I mean, I think
if you ask them privately, nobody will express a very strong belief that it will end at some point. For example, this is maybe a pedantic point, right? Suppose you're trying to understand the structure of an atom, right? So there are various rules for how the shells of an atom fill up, right? There's something called Hund's rule, there's something called the modeling rule, and so forth, right? None of these are mathematically understood. None of them can be derived from Schrödinger's equation at the moment. Right? So that's the level at which we don't have a precise understanding when you try to apply the fundamental theory of physics to actual phenomena. Right? And you might have QCD, which is the theory of quarks and so forth, right? But nobody uses QCD to understand nuclear physics. You have a separate model in order to do that, so an approximate model, and that's what most of actual physics is like. So to hope that just because we understand something about so-called 4 fundamental forces, everything else will be understood, this is a grand illusion.
Yeah, but I do wonder if there will then be a lot of filling in of holes and gaps and so forth, but you can envisage a point in which we know how it all hangs together up to some level, and then of course you can take it to level up beyond that and look at quantum chemistry, and then sort of how do cells form and so forth. But it kind of starts to become other subjects, I guess.
I think that, so I don't really know, of course, but my feeling is that in there is a kind of arbitrary division, meaning division between something you regarded as fundamental and some other things you regard as just gaps and holes. And I don't think the structure of our knowledge really divides up in that way. It's not as though... I mean, this is true even in mathematics, right? Suddenly this came to mind. I hope it doesn't seem too irrelevant to you. But you probably know any mathematics paper is full of mistakes. Anything mathematics paper in current journals and other than the most elementary subjects are full of errors.
Okay.
And now most mathematicians regard most of the errors as being kind of inessential. They are things that can be fixed easily. But which things are inessential and which things are not is also sort of an arbitrary choice that you make. And in order to justify your sense that something is essentially correct, there's nothing you can do but rely on a kind of community consensus. There are no objective criteria for doing this, right? And so I don't think there's any way to escape the idea that even in mathematics, most of our knowledge is approximate. Yeah. So some notion of approximate truth, for example, is unavoidable when you think realistically about the way mathematicians practice and the way the subject evolves. But interestingly, in my conversation with philosophers, they are remarkably resistant to this idea. They are much more attached to the idea that mathematical truths are about certainty than a practicing mathematician is. Right? So that's a kind of interesting thing. But so I think in practice, it's hard to imagine any kind of completeness of understanding being achieved, even with existing mathematics, not just mathematics that's going to be developed, because we'll keep on recasting the same objects and improve our understanding, and then it'll be connecting to some other things and so on. So this is one of the many senses in which I think the story is continuing. You probably know this idea. This is kind of a very stupid example of such a thing, but you know this idea that the theorem of Pythagoras, for example, is wrong.
No, okay.
This is a completely obvious thing if you just look at it from a certain point of view. It's because according to relativity, the assumptions just don't hold, right?
Yeah. Okay.
If you created an actual triangle, the right-angle triangle, right, and measured A, B, and C, right, the more precisely you measure it, A squared plus B squared will not be equal to C squared.
Yeah. Okay.
So from that point of view, it's wrong.
For the actual space that we live
if you
in.
take it to the theorem to be one about actual triangles, right?
Yeah.
Even in an idealized sense that we can construct in our actual world, right?
Yeah.
On the other hand, if you take it to be just A implies B, it's probably correct, although again, one never knows how examination of the assumptions will evolve over time, right? So any given mathematical result, again, has many different interpretations when you try to start discussing the correctness or not, right? And this is just, it just suddenly came to mind as one aspect of the fluctuating nature of the achievement or knowledge that you get in mathematics and how it changes with time.
Yeah. I think it's nice to imagine that maybe mathematics is a subject where you can make progress, and yet the progress will never be exhausted.
It's also hard to know what you mean by progress.
Yeah.
So somehow these are all things about which you make human judgment.
Yeah.
And there's not an objective criterion for it.
Well, this has been such a wonderful discussion.
No, thank you so much for your question.